Hello and welcome to your video about steel, and in this case just sort of steel the product. We've gone deep on the chemical structure and how to change it through heat treatments, but what we want to talk about now is sort of the finished product and things that can happen to it and how we use it to supplement what you're doing with your reading and your homework. So the Golden Gate Bridge, what a beautiful image of steel. It's such an iconic structure, but it also highlights one of the greatest challenges of steel. So let's zoom in on one of the horizontal members in the tower. We can actually see that there's a lot of rust starting to happen there and coming through the paint. Now, this rust really isn't that bad. We actually saw a great example of rust on a field trip to Granite Rock's cement batch plant, where they had an underground steel hopper under where the train tracks deliver their aggregate onto a conveyor belt. As we zoom in, we can see that that steel is just peeling apart almost like an onion. So obviously it's caused great corrosion and damage to the steel. And rust really is nothing more than corrosion. Those two words are used interchangeably. And the problem is this rust or corrosion really can weaken the structure. And in 2016, it was reported that there was $1.1 trillion in cost in the US due to corrosion, and worldwide that was $2.5 trillion, which is just crazy. Now, it's not surprising that steel wants to rust because steel, as we've already learned, is mostly iron with some carbon inside, but that iron is actually coming out of the ground as iron ore. And that iron ore has to be heated to very, very hot temperatures to get the oxygen out of the iron ore to turn it into just straight iron. But iron is stable and wants to exist in nature as iron ore. It wants that oxygen back. And so corrosion is just a natural process, or rusting, that iron wants to go through. And so what is required for corrosion, we actually see that there are four things that must be there: an anode, a cathode, a conductor, and an electrolyte. Now, you might remember from chemistry or physics that an anion is negatively charged and a cation is positively charged, and you're remembering correctly. But when we talk about an anode, that is the positively charged or positive electrode where the corrosion occurs, and it's losing electrons as part of the corrosion process. The cathode is your negative electrode that's needed for electric current, so it's taking the electrons and they're traveling through the cathode to the cathode. You have the conductor, a metal pathway, right, that allows the flow, and then your electrolyte. In this case, it's the liquid that supports the flow of electrons from the iron to the oxygen. In steel, we have 1, 2, and 3 present, and all we really need is the moisture, which is in the air. But it's important to note that pure water isn't a great electrolyte. Typically you want contaminants in that water, but if you're near the ocean, you have salt, which accelerates the corrosion process. You can also have acid rain, just any pollutants in the air that the water brings down, and all of those things add to the liquid's job or the liquid's potential as an electrolyte. So how do we stop corrosion from happening? Well, to be perfectly honest, you don't stop it, but you can help control it and slow it down. The easiest way to do it, the least expensive, are going to be some sort of protective coating that isolates the steel from the moisture. So the simplest of that is just going to be plain old paint. And you can paint something and it will protect from the moisture, but of course the painting is not durable, especially under UV. It's going to peel, it's going to come off, and so you're constantly repainting. You can get a little bit better performance if you use a primer that is rust prohibitive. So we've heard of Rust-Oleum paint, right? And they have these additional pigments. They go to the steel surface and they help reduce its behavior to be able to transfer those electrons to have that anode-cathode electric conductivity path. We can take it the next level, and these are called sacrificial primers. So zinc is one of these amazing sacrificial metals that it actually will, it's a more active metal, so it will give up its electrons that are trying to move from iron over to oxygen. It will give them up before the steel has to, or it will give its electrons to steel. And so it will degrade first. So it's considered that sacrificial layer. And it's called galvanizing primarily. So you may have heard of a galvanized bucket, or we saw the galvanized handrail in the video. And so that protective laying, and you hot dip your metals is typically how it's done, or it's a spray-on coating during the manufacturing process. Now, these are not our most expensive methods, but the thing is you have to understand that we can only save 15 to 35% of corrosion costs by using protection because the protections themselves also have costs. All right, so painting. We talked about painting, and here we are painting the Golden Gate Bridge. If you were not aware of this, the Golden Gate Bridge is being painted just darn near every single day of the year. It's a continual process. We move from end to end of the bridge. What they actually do is they will build up in certain areas protective barriers to protect the workers and also to protect the drivers on the bridge, and they will sandblast. They will do things to get a lot of the pits out of the steel if they have to, local repairs. Then they come back with a primer, and it turns out they use a primer that is filled with zinc to act as that sacrificial layer. After they put on the galvanized based primer, then they come back and paint it the famous international orange color that was picked by the original engineer with the idea that it would complement the green hillsides of Mill Valley and the Marin Headlands and also the blue ocean. Now, one of the more expensive methods we can use is the cathode protection. And so what cathode does is you literally run a continual current through your structure. It's a low-grade current. It's not enough to shock anybody, but that current is constantly supplying electrons, and they actually will recover your metal surface such that you then are not losing electrons from your metal. And so you just don't get that anodic reaction. Instead, you get a cathodic reaction where the oxygen is not taking electrons from the steel. And what that might look like is literally a ground conductor. You have something putting charge in. This is not a cheap way to go, but for underground structures, it's going to be a way that you can have long-lasting protection for something that's very hard for you to inspect. Anode protection, this is really cool. So here's another type of protection you can use. You actually attach more active metal. So the light gray discs that are attached to the ship components there, the propeller and the hull of the ship, those are more active. They're going to corrode first. So they actually give up their electrons to steel so that steel isn't giving up its electrons in the rust process. And then when you pull a ship into dry dock, you can just pull off the eroded and corroded anode protection that you put on and just put new ones on. Really cool, not as common in buildings as it is in, say, shipbuilding. And something that's a little more modern, but really cool is high performance steels. If you're at an industry, this is going to be called Core 10 steel. Nobody calls it HPS, but that's sort of the more global name. Its street cred name is Core 10. And what happens in these steels is you actually have alloys that allow the steel to rust. We still have it rust, and it's actually considered kind of cool and aesthetic. It starts becoming part of the design, but that layer of rust creates an oxide layer that inhibits any additional rust from occurring. It's expensive, but it's cool. Now, to get the different alloys, say, of this steel, or to look at the behavior of steel, it is always good to understand the chemistry of steel. This is out of your textbook. There's additional tables in there, but a more basic thing, we can see carbon, the highest percentage being only 0.3% carbon, which is in a mild steel. But we also are adding things like copper, manganese, potassium, you'll see sulfur, but you might think things like chromium. Chromium is going to give you your stainless steel or your chrome, or molybdenum or vanadium or nitrogen. So there's a lot of things that get added into the steel formulas, and there are thousands of formulas for steel. And when we talk about steel, it's good to talk about the durability. I mean, that's what we've been talking about here, right? Is the durability of steel. Well, in fires, steel is not very durable because the high heat causes it to change mechanical properties and lose strength. This is actually a photograph after a fire, and you can see the steel beams in the background there like spaghetti. And interestingly enough, here's an older photo, and you have a very large wood member. Very large members of wood in high heat tend to char on the outside. That char creates a protective coating, and it takes much longer for them to burn. And here you have the remnants of a charred wood beam still carrying the deformed spaghetti-like steel beams that used to carry the structure. Now, there's a reason these are very old pictures, and that's because today you've got to have fireproofing on your steel. That is required by code. These are actually from the Sobrato new STEM building. And so on the right side, the beams have all been sprayed with fireproofing. And on the left side, you can see the beams up in the floor above, and they're still the painted rusted coating red color. It's not rust, it's a paint that's put on as protection as they leave the manufacturer. But they have not yet been sprayed. So they're in the process of doing the fireproofing in the building. And so it's great because you can see the transition from fireproof to not fireproof. Now there's three types of steel that we really use in civil engineering, and there's going to be our what we call structural steel. These are the big wide flange beams, the tube steels, the channels that are all that hot rolled steel. So it's shaped while it's hot, while it's still in that red hot. You can pound it or force it through rollers to get the I shape or the H shape or the C shape. Your structural steel can span really long distances. It allows you to have large open spaces that you can come back in with partition walls to break up for offices, but then open back up with minimal costs for remodeling, which is great. So it can give you a building that's easy to remodel. Construction goes up pretty quickly because after the design, the drawings are actually sent to a fabricator and a ton of your pieces are cut in the fabricator, bolt holes drilled, plates welded on, and then it's brought out to the job site and almost put together like an erector set. Cold form steel is that rolled out sheet metal, and then while it's cold, it's actually cut and bent into different forms. And what's common now is to basically put it in the shape of what would be a 2x4 or a 2x6 wood stud and use it just like you would with wood framing. We're seeing more houses out of cold form steel, but where it really is most common is if we go back and think about our structural steel. If you're going to build intermediate walls or you need the exterior walls to put your windows in or whatnot, then you can do it out of the cold form steel, and then that's easy to remove and put back in as you change things. And so this would be what your partition walls are made out of. And finally, reinforcing steel. We need a lot of reinforcing steel in our concrete to make it safe. So that's your just big picture on steel, mostly on what are our concerns using steel, so its durability, either from fire or from corrosion, and then of course the three main types of steel used in civil engineering.